Hello, it's Malcolm here, and in this screencast I'd like to talk to you some more about the way mathematics is applied to the real world. For most of you, the experiences you've had up until this course was that you had a specific piece of maths and you learnt an application of that maths. For example, if you had addition, you learnt how to use it to add up your grocery bill, for example. So you were using your maths, but you were using it in a real world context. We then had a little bit of a discussion in our last couple of classes about how applied mathematicians might think of the way they work, and we said that mathematicians think that they do their work by modelling, and they use the model to better understand that situation. And the kinds of reasons that we might undertake that modelling, the kinds of things we might try to understand, we discussed the things like testing, predicting, exploring and explaining. And the examples that we've seen so far have done each of these things, but all of the examples we have seen so far have been with respect to a specific context. So even though we didn't know necessarily what maths we were going to use, we had the one context in mind. And what I'd like to talk to you now is about a spectrum of applied mathematics problems. And so we have been working down at this end here, down the situation-specific problems. And I'm saying that in our spectrum here, we can go from situation-specific right up to what I will call broad process problems. And I'll come back and talk about that in a minute. And of course, the other dimension here is that we could have exercises, and so here situation-specific exercises is what most of you had experienced so far. We've moved down now to situation-specific problems, but we'll come down to the problem end of the spectrum. And what I want to do is move over to here. But before we do, let's think back on the applied problems that we handed out in class the other day. Where would we put something like locating the depot problem? Well, to me, it would go down here. It's situation specific. We wanted to know where would Bob de Baker locate his depot. So that was specific to Bob and his situation in Merriweather. But down here it's a problem. We don't necessarily know straight away how to go about it, what factors to include and so forth. And likewise, the blind spot problem and the cereal box problem. The cereal box problem may be not quite as specific as located in the depot, as in this might apply to any cereal box manufacturer, perhaps. So I might move it along the spectrum here a little bit more, but basically they're situation-specific problems. What I want to do is move right down to the other end here and talk about broad process problems, because that's at the far other end of the extreme, but mathematics is still extremely useful there. So let's do some sorts of, just before I move on, these arrows here. When we did our cereal box problem, we started off and said, okay, we want to solve the problem just for the particular firm we're in, but being mathematicians, we tried to generalize our results so that they could work not just for 8 figurines, but for 16, for any number of figurines. And so we tried to generalize the problem. So we tried to make it broader. So nearly all the time, we might start off with a specific situation-specific problem, but we will try to move in this direction of making it more broad. Likewise, over here, when we get back to it, when we're talking about our broad processes, we start over there and then we'll quite often want to apply it to a specific situation, so that will move backwards. So there's going to be an interaction there. But let's go and have a look at some of these broad process problems. So an example of a broad process problem might be, I want to understand about bushfires. That doesn't say I want to understand a specific bushfire. I don't have any particular one in mind. I don't have a particular location in mind. I just want to have a general understanding of bushfires. Now, there are lots of ways of doing that. You can go and study bushfires. You can go and take videos of bushfires and so forth. But mathematical modelling can also help us understand bushfires. The kinds of questions we might ask is, well, what can I do? What sort of strategies can I do to help prevent bushfires occurring? So am I better off clearing the trees? Am I better off having a controlled burn? And so forth. There'll be a whole lot of different strategies that you could try. So you could actually do a mathematical model here with an aim of exploring what would happen in certain scenarios. and so on. So understanding bushfires to me is a broad process problem. Another example might be understanding population dynamics. What are the factors that might affect how a population grows or dies, and so on? This can be relevant to us as humans, the human population on Earth, or it could be relevant just to the bacteria living in a dish in the laboratory. Could be pertinent to, say, pests or wildlife, for example. So how do we handle the rabbit population, and so forth. So that's a general process, but we're not thinking of any one particular situation or context. But of course, once we've done our general model, we would try to apply it and see, does it apply in specific situations. So with that one would work backwards. Another example might be understanding the spread of diseases. What can we do to prevent the spread of diseases? Now, again, we don't have a particular spread in mind, we don't have a particular disease in mind, but we might be able to do some general modelling that helps us understand the spread of diseases. So to give a little bit of an example of this, let's pick the middle one here about population dynamics. And so here, understanding population dynamics. So let's start off with a simple theoretical model. And your model in here, so we're trying to explain why things have happened or understand what's happening here. So we're going to make some assumptions, and we're going to make this first model really, really simple. So we're going to assume that the way a population changes at any time is proportional to the size of the population. And that's it. That's going to be our model. So we're trying to explain how populations grow or the dynamics of populations just from that one assumption. Now, of course, that's going to be way too simplified, but it's a good spot to start. And those of you who have done any calculus would recognise that this gives rise to a differential equation, which is very easy to solve. And the solution of that differential equation, in fact, gives us a graph, and it says that the population would grow exponentially with time. So if there are no other factors involved, the population will grow exponentially. And of course, that is actually quite true in the early stages, say, of growth of bacteria in a controlled environment. Eventually, of course, what happens is that other factors become into play. For example, you might start running out of food, you might start running out of land or whatever. And so therefore you have to go back and change your model, make it more complicated. But there is a very simple theoretical model. Let's go along and now have a look at a simple simulation model. So let's make this one a little bit more complicated, but not too complicated. So here, let's assume, in this case I should call them wolves and sheep, but it could be any predator and any prey situation. So here we go. We're going to make some assumptions, and to make our simulation work, we're just going to make these assumptions. So wolves and sheep wander one step per time in a random direction, and each time they take a step, that uses some energy. Once you lose all your energy, it dies. So how much energy they've got, of course, will be an input. Sheep eat grass to replenish their energy. Wolves eat sheep to replenish their energy. And we'll say a wolf eat a sheep if they happen to land on the same square at a time unit. And grass replenishes at a fixed rate. So we might say, oh, it takes 3 time units for the grass to replenish itself. And lastly, wolves and sheep reproduce with a fixed probability each time unit. So we might say 20% of the wolves have babies, 20% of the sheep have babies each time unit, or something like that. So there are our simple assumptions. What sort of things can we do from that? What can we actually understand? So let me show you a simple simulation that's done in the program NetLogo. And I talk about NetLogo in the technology section. I don't expect you to go on and use it, but if you did, it's a lot of fun. But let's have a look at that. Okay, so here's our NetLogo screen, and it looks quite complicated, although it's not that difficult to do. But in here, these are all the parameters that we've got. So here's the one parameter is how many sheep did you start with. Another parameter is how many wolves did you start with. How much energy does the sheep gain from food, and so forth. So these are all inputs to the model. But for the moment, Oh, and over here, a green square means that there's grass on the square. A brown square, excuse me, means that the grass is eaten. The white one is a sheep, the black one is a wolf. So there are 50 wolves distributed randomly and there are 100 sheep distributed randomly. Let's run our model and see what happens. So here we go. And there's our model running. The sheep are eating the grass, the wolves are eating the sheep. And if you look down here, you can see that there's about 160 sheep, 120. So the population of the wolves here, population of the sheep, I should say, goes up and down. The population of the wolves go up and down. So what this model says, under the circumstances, under the assumptions we've made, it looks like the populations continue to live, but it's cyclic. So as the number of sheep go up, the wolves get to eat them. As the number of sheep goes down, the wolves don't find them so easy to eat, so they don't get as many. And so that's how that one works. Now, let's make some change. Now, the beauty of a simulation is that we can now make some changes. So let's imagine that we have a drought, and so the grass doesn't grow back so quickly. So let's make the grass regrowth time, say, 60 time units rather than 30. Now, what might you expect to happen in this case? We might expect that if the grass takes longer to grow, the sheep won't find as much grass to eat, and so therefore the sheep would die off. So and I guess if the sheep die off, the wolves have to die off as well. Once the wolves die off, then we probably expect the sheep to grow, the population of the sheep to grow again. So let's have a look and see if that's what happens. So go. So here, the sheep's growing, it comes down. Look at this, the wolves are dying off. So the wolves died off. That's a surprise, isn't it? The wolves died off. And yet the sheep were nice and cyclic. Let's run it again. That might have been, let's just run that again. Do it again. So the grass is taking a long time to grow back, so the grass is dying. The sheep population isn't as high as it was before, and the wolf population goes down. And eventually the wolves die off. So, to me, that's a little bit of a surprise. That would actually make me start to think what's going on in here. But you can start to see in here that this is a very, very simple model, of course, a very, very simple simulation. But by playing with the parameters to the situation, we can get a broad insight into a very broad process. And we are not trying to apply it to any specific population, but we probably could apply the principles to a specific situation. And an awful lot of applied maths is done that way. We probably won't do much of that in our course, but it's good to know that that sort of thing exists. And if you want to have a go at it, well, the tools are out there for you to have a go. But we'll leave it there for the moment. Thanks.